So thanks again for being here. So the topic, as Stefano was saying, is basically cosmology meets particle physics. So how you can constrain particle physics properties, quantities with cosmological observations. Okay. So let me start with some very general considerations about why you can do that. So the universe today is today means 40 billion years after the Big Bang, or more precisely after the end of inflation. So the universe today is very, very cold. Okay, it's at 3 degrees above absolute zero. It's nearly empty, meaning that the energy density is 5 × 10⁻⁶ GeV per centimeter cube, which is the equivalent of 5 proton rest masses per meter cube. Okay, so the energy density is really small. However, we know that the universe is expanding. So if you play the movie backwards, you expect that the things, let's say, are becoming more and more closer as you go backward in time. And in particular, temperature and density are bound, at least in principle, to grow arbitrarily large, again, in principle, as time goes to zero. I mean, as you go closer and closer to the initial singularity. And so this is a very nice plot. I mean, it's some infographics in some sense that was made in the 80s, so a while ago, by Mike Turner in Chicago. And you can see here we have several scales here that give you, so we are here, this is the present time. So again, 14 billion years after the Big Bang, and you can see the corresponding temperature, energy, and density. Okay, and again, you see that as you go backward in time, the temperature and the energy are increasing. Okay, so you go through the atomic binding energy first, which is the time of cosmic microwave background decoupling, then the nuclear binding energy, then you go up to TeV, so this is the energy scale of LHC, and above, and actually the maximum temperature that you can reach depends on what was basically the energy scale of inflation and how efficient was the reheating that happened after inflation. So if you want to be very conservative, let's say that we know that at least the universe went through an MEV phase, because we were able to form, the universe was able to form light elements. Okay, and you need again the temperature of the universe to be of the order of MEV to form the light elements. But we think that actually the universe also underwent some phases in which the temperature was higher than that. So the point is that in some sense the universe acts as a poor man's accelerator. Okay, so you are able to access again a regime of very, very high energies somehow for free. Of course, it's nothing is really for free. Of course, again, this comes to a cost, apart from the cost that you need in any case to observe all these things. And the cost is that, of course, you're not in the controlled environment of an accelerator, of any way of a laboratory, of a beam dump experiment, for example. But basically, you have to take what you get. Okay, and again, we're going to define all these better in a second. And this is defined somehow. There is a process that the United States undergo every decade, which is basically the building of some roadmap for particle physics. This is called P5. And not at the latest, but at the second to last, let's say, P5 process, the US, they defined 3 frontiers, okay, for high energy physics, which were the intensity frontier, which is basically what you do at the energy frontier, which is what you do at the LHC. So you try to reach higher and higher energies to unlock new physics at those energies. You have intensity frontier, in which you try to produce more and more intense beams, again, to look for new physics. And the other one is the cosmic frontier, in which, again, you use the universe as an accelerator, I mean, as a way to access high energy physics somehow for free, again. And this is a nice definition that I stole from the Fermilab website that says the experiments at the cosmic frontier take advantage of naturally occurring events to observe fundamental physical processes that are impossible to investigate in terrestrial laboratories. So there is a nice complementarity between these three frontiers, or if you want, between what we do in the lab on Earth in various ways and what we can do through cosmological observations. Now, one thing I'm trying, since there are many students, I'm trying, at least the first part of the talk will try to be quite pedagogical, so that things don't look exoteric, or at least not too much. So, I mean, someone might be bored here, but I think it's useful. So, I told you the universe is an accelerator in some sense. Now we need the detectors. Okay, so how do we access the information that is somehow hidden? Okay, in this timeline here from today to the very early universe. So the point is that in cosmology, most of the time, our experiments, they do observe random fields projected on the sphere. Okay, let's say that projected on the sphere for us is maybe a complication, but let's keep that in mind. So again, we observe realizations of random fields on the sphere. So then we have a field which might be whatever we can measure. So if you want to make a concrete example, think of this field here, this phi, might be the temperature fluctuations of the CMB, or maybe the number of galaxies, the density of galaxies at a given point in space and time. So again, this is a field defined in position and at a given time. Usually we look at this in Fourier space, so this is the Fourier transform. And this the field, again, at a given time, you can write that as some initial conditions, okay, evaluated at some early time, and these are usually set by inflation. And these initial conditions are also usually expressed in terms of some other field. This is usually the field of curvature fluctuation that you have at the end of inflation, times a transfer function that basically tells you how those initial perturbations have evolved until time t. Okay. Now the stochastic part here is in the initial conditions. Okay, the initial conditions are stochastic. We don't know how to predict the exact pattern of the initial field. Okay, so we will see that in a second. So we will just use the stochastic properties of the field, while the transfer function is deterministic. Then, of course, this is T of phi, if you want. Okay, that depends on the particular field that you're looking at. Okay, now the complication. Of course, this is again a field in time and space. Of course, we observe this field now and here. Okay, so this means that what we're actually seeing is this field at T0. Zero in cosmology means the present time. Along the light cone, okay, because of course we are not able to see all space at any given time, but we can only see what has emitted light or whatever. Usually you're looking at light, so you're really looking along the light cone. You can only see things that are have emitted light at a given time, such that given their distance, the light has reached us today. And then you can write this. So this is what is actually observed. So this is a field which is a function of angular direction, okay, n today. And you can write this basically as a line of sight integral of the 3D field times a window function that basically tells you how you are picking the three-dimensional field. It's acting as a filter in some sense. Okay, now more in schematically, which is really what is useful for us. You have this two-dimensional field is somehow some convolution, okay, of some initial conditions which encode some, let's say, inflation, or in any case, some very early universe physics that, again, set the initial conditions, times some evolution encoded by the transfer function. And this depends on many things, actually. This depends on the expansion and thermal history of the universe, so how fast the universe expanded, and how the various species that make the matter energy content of the universe evolved from a thermodynamical point of view. So this means that this evolution here is sensitive to the matter energy budget of the universe. For example, how many baryons you have, how many very light relativistic particles you have, and so on, and also on the microphysics, so on the way in which these particles interact. And then you have projection effects, okay, which in turn tell you something about the geometry of the universe, and again about the expansion history. Because again, you are projecting things that live in configuration space, in real space, on a sphere. So depending on how far you are from a given object or from a given typical length, this will be projected on a different angle. So all this, so you have lots of information here that, of course, they all get folded together, okay, in your observable. Now, the very last thing to understand here, okay, no, before that, so to be again more concrete, for example, an example here would be the observations of the cosmic microwave background. You know that the cosmic microwave background is a relic radiation that was emitted roughly 400,000 years after the Big Bang, when the universe became transparent to radiation. It's a thermal radiation, it's a black body, which is isotropic to a very high degree, but it has tiny anisotropies. And then again, that field phi there in the previous slides might be the field of temperature anisotropies, of the intensity of the CMB radiation, of the polarization, which is actually two fields, because you can decompose the polarization, which is a tensor field, in a curve-like, which is the B modes, so-called B modes, and in a gradient-like component, the E modes. Or you're also sensitive somehow to, these are called the lensing anisotropies, and this is a measure of the gravitational potential integrated along the line of sight. So this is to make a concrete example. And then, of course, in each of these cases, you have that this transfer function here, okay, will be different. So each of the transfer functions will be sensitive to different properties of the universe. Let me just tell you that for the temperature anisotropies, since we are here, the temperature anisotropies have been measured by the Planck satellite. So there are some young people here. So Planck was a satellite that was operative in the early 2010s, which mapped the temperature anisotropies to the cosmic variance limit, which means basically as good as we can, given that we are dealing with a random field. It also measured the polarization anisotropies, but again, not to the same precision as the temperature anisotropies. So this is the target of the next generation experiments, and also measured these lensing anisotropies, again, not to an extreme precision. And this is also another target for the next generation experiments. And these are important for us, especially for neutrino masses, as I will show later during the talk. Another example of observables is what you get from galaxy surveys, like Euclid, for example. So here you basically have two distinct two things that you can. Okay, there is something wrong there, but anyway. So in a galaxy survey, you map the distribution of galaxies in the universe, not just the distribution. You can also measure the shapes of the galaxies, of a large number of galaxies. And here, that field phi might be, for example, the galaxy number counts. So this means, again, the number of galaxies at a given point, the density of galaxies at a given point in space, as well as the cosmic shear, which is some field that quantifies the distortion of the shapes of galaxies due to the fact that you have intervening matter between us and the galaxies, which is typically dark matter. And this has a weak lensing effect on the shape of the galaxies. So the shape of the galaxies get distorted, and you can somehow extract this field, okay, this shear field, and again use that to extract cosmological information. Okay, now, as I told you at the beginning, the observed fields are stochastic, so we can predict only their statistical properties. The very first thing that one uses is the two-point correlation function, or its harmonic counterpart, which is the power spectrum. So what you really measure, or let's say what you really get, are able to give theoretical prediction for is the two-point correlation function, or the power spectrum, which again is the expectation value of the product of two fields don't need to necessarily to be the same field. I mean, this phi A might be the CMB, and phi B might be the galaxy number counts at two different directions, and you average over all possible directions. You can do this in real space again, and this is the 2-point correlation function. So you can do that in harmonic space, and this is the power spectrum. So since you get prediction for these quantities here, you extract these quantities here also from the observations. Okay, so we have observed the power spectra, which is what your data look like. Let's say your processed data look like. Okay, now this is kind of a repetition, so I'm not really staying too much on these slides. Just to tell you that, I mean, for the CMB, exactly, this is what you will get when you do this compression of the information. Okay, so again, the CMB, as I told you, it's 3 fields. Okay, the temperature and the 2 components of polarization. So you can do there are 6 possible correlations. Actually, 2 of them are bound to vanish if electromagnetism conserves parity. So you end up with this TE, and again, this is what Planck has measured, okay, the red dots with the very small error bars, and then you have the best fit. And actually, from the polarization and temperature map, you can also get the power spectrum of the lensing fluctuations. Now, getting back to this image here. So let's focus, for example, for a few slides on what happens here, okay, around MEV. MEV, the MEV era is particularly important for neutrinos, which are the main topic, okay, of this talk. Why? And we shall see that in a second. So let's start at a temperature which is a bit larger than MEV. The exact number is really not important as long as it is below 100 MEV. And I'll tell you why. So you understand that since this is the temperature of the universe, so this is a thermal bath at that temperature. So at any given temperature, you would expect to have all the species in the standard model with a mass that is larger or of the order of this temperature, the equivalent energy, okay, to be present in the thermal bath. Okay, so if you are above 1 MeV, you certainly have but below 100 MeV, okay, then you have all the species in the standard model which have a mass that is larger than 1 MeV but smaller than 100 MeV, and this is the photons, the neutrinos, and positrons and electrons. Okay, that's it. So the reason why I'm putting my boundary at 100 MeV is that then above 100 MeV you have muons as well. We don't need to go that far, okay? So let's say that we start above MeV, and then we have this universe, which is a thermal bath, which is filled by a thermal bath of neutrinos, photons, and electrons and positrons. Okay. Now, what we want to know, we want to ask, what's the thermal equilibrium? Okay, what are the conditions for which thermal equilibrium between these species holds? And thermal equilibrium in cosmology, in the expanding universe, is basically a competition, okay, between some interaction, which in our case is weak interaction, because neutrinos they're not interacting with photons, okay? They're interacting with electrons and positrons through the weak interaction, versus the expansion. Now, the interaction rate for weak processes is roughly the Fermi constant squared times temperature to the 5th. This is really a back-of-the-envelope calculation, okay? You can do this more precisely with all the right factors, but this is basically the story. The expansion rate, so the Hubble parameter, is proportional to the square root of the Newton's constant times t squared. Okay, so you see that here we know everything. There are no unknown quantities. Okay, so all these only depends on the Fermi constant and on the gravitational constant. Now, if you look at the gamma over h ratio, this is T over MeV cube. So what is this number here? So this is, again, the interaction rate over the expansion rate, or if you want, this is the number of interactions per Hubble time. Okay? So this means that in the typical time of the expansion, you have gamma over h interactions. So you see immediately that when T is much larger than MeV, you have lots of interactions between neutrinos and electrons, and you expect this to keep thermal equilibrium. But as long as the temperature goes down MeV, basically neutrinos, they don't interact anymore. We say that neutrinos decouple. Okay? This has two important consequences. One is that the thermodynamics of the two species basically becomes independent. Okay, they're not in thermal contact. Okay, so they don't talk anymore. And the other one is that neutrinos they start to do what we call free streaming. So they are free particles. Okay, so they move along geodesics, and this has important consequences for structure formation. Okay. Now there is one more thing that happens slightly after neutrino decoupling, and this is the fact that since neutrino decoupling happens so close to the energy threshold for the creation of electron-positron pairs, which is half MeV, the mass of the electron, you have that a very short time after neutrino decouple, electron and positrons, they do annihilate away, and they inject entropy to the photons. So what happens is that this is the temperature of the species as function of the cosmic scale factor. So you have that the temperature of the neutrinos goes down the inverse of the scale factor. The temperature of the photons has some transient, okay, corresponding to the electron-positron annihilation. When it gets heated, it's not really heated, it's going down anyway, but I mean, it goes cools that the photons cool down a bit more slowly than the neutrinos. Then after electron-positron annihilation is over, they go like the scale factor to the -1 again. So these two curves here, they are parallel, okay? So they start at the same point, okay? The plot doesn't go up here, but if it could go up here, you just see one single line. So they go down, the neutrinos go like this, photons get heated, okay? And then they start to go parallel to the neutrino. So this means that we have a constant ratio between, after the electron-positron annihilation is finished, we have a constant temperature ratio between the two species. And you can compute this, it's quite easy actually, using entropy conservation. And you get this, let's say, magic number, okay, which is 4/11 to the 1/3 for the ratio of the two temperatures. So the neutrinos are colder than the photons for the reason I have just said. The point is that we measure the photon temperature because this is the CMB temperature. So we know that today this is 2.7 Kelvin. So if you put the numbers, this T nu is 1.9 Kelvin. Okay? Now this means that you have basically everything that you need, again, without any free parameter, to compute some quantities relative to the neutrinos. As I told you, temperature is 1.9 Kelvin, which is roughly 10 to the -4 eV. The number density, these are fermions at equilibrium, okay? So you can, again, this is only defined by the temperature. The number density is 100 particles per centimeter cube per neutrino species. For comparison, photons have a similar density, no surprise, because they are also at thermal equilibrium, roughly at the same temperature, which is 400 particles per centimeter cube. So neutrinos, they are actually the second most abundant species in the universe today, the first being the photons. So we call these relics of neutrinos the relic neutrino background. So again, this is just a summary what I just said. I mean, I think the take-home message here is that the presence of these neutrinos is a very basic prediction of the standard cosmological model with no free parameters. Okay, again, it's just weak interactions versus gravity. We know weak interactions, we know gravity, okay, and there is nothing that we ignore in this calculation. Or let's say there is one thing that we do ignore that didn't enter the calculation so far, which is the mass of the neutrinos. So everything, the decoupling happens at very large temperatures where neutrinos are effectively massless. So we don't need the mass to make the calculation. But today, the neutrinos are very cold, okay? Because again, that temperature there is 10 to the -4 eV, then the mass enters into the late time cosmological evolution. And that's actually the reason why you can constrain the neutrino mass with cosmological observables. Okay, let me introduce one last concept, which is very important. So you can write down the density of neutrinos. The total density in what cosmologists call called radiation, which means very light species, maybe massless. You can write the density of light species at 3 times. Okay. Now, if you write these again at temperatures which are slightly above MeV or below, this is just the neutrons, and after electron and positron annihilation, let's say this is just the neutrinos and the photons. So you can write this immediately. So you can normalize to the photon energy density. So you have 1 for the photons, okay, and the neutrinos will weigh 3, which is the number of neutrino families. 7/8, and this is a factor that comes from the fact that you have Fermi-Dirac statistic and not Bose-Einstein. And then you have this magic number again to the 4/3, because the energy density was like the temperature to the 4th. So again, this is a fixed number. Now, cosmologists actually like to turn this the other way around and write this into a definition. So this is dangerously similar to the expression in the previous slide, but it's conceptually very different. Okay, so here again, this is a definition. Here I'm saying I'm writing I'm parameterizing the energy density in radiation, so in light particles, through a parameter that I call an effective, which is called the effective number of relativistic degrees of freedom. This is the right name for it. So what's the reason for this? The reason is that in the picture that I just said, an effective is equal to 3. Okay, so this is effectively a way of measuring the energy density of relativistic particles in the early universe, normalized to the energy density of a standard neutrino. So if you want, in some sense, I can compress my measurements into a measurement of this number and check whether the picture, that I have just described is compatible with the data or not. If the picture is compatible with the data, I'm expecting to get something that is should be 3 within the uncertainty. Now, actually, the real, let's say, standard prediction is not 3. It's actually this number here. This is a very dense slide. I'm not commenting too much into that. But again, the take-home message here is that the standard model prediction for an effective is actually 1.5% larger than my naive computation would predict. So it's 3.44. This is a theoretical error. Okay, this very small error here is a theoretical error. So what's the reason? The reason is that when electrons and positons annihilate, one of the reasons is that when electrons and positons annihilate, neutrinos are still in thermal contact with the photons. Thermal contact is not something that goes on and off abruptly. Okay, so the neutrinos, they decouple in a finite time. Okay, so when electrons and positrons, they do start to annihilate, there is also some small degree of thermal contact between between electrons and positrons and neutrinos. So the entropy of electron-positron annihilation doesn't go 100% into the photons, but also goes into the neutrinos. So we have a small heating of the neutrinos as well. So that's why you get this number. Okay? And I also like to say this, first of all, because you will see comparison with the 3.44 all the way down until the end of the talk. And the other thing is that one of the first person to compute this number was our Sasha Dolgoff. He was here in Ferrara. And I think this was definitely more than 20 years ago. It was early 2000s or maybe even late 1990s. And then again, this has been refined. There are several groups that do the computation independently. They all agree on this number within, let's say, this theoretical error. Let's say that this theoretical error is somehow an average of the uncertainty reported by the various groups. Okay, now we can write down the energy density of neutrinos today when neutrinos are non-relativistic. So you can write down the density parameter. This omega here is, as usual in cosmology, a ratio between the present energy density and the critical density, which is the density that you need to make the universe specially flat. Again, since neutrinos are non-relativistic, this energy density is the mass times the density. And again, here the only unknown quantity is the mass. So you can write this very handy formula, which is that the omega nu h squared small h is the Hubble constant in units of 100 kilometers per second per megaparsec. So it's the sum of the neutrino masses divided by roughly 100 dB, dB. Now, what do we know about neutrinos from laboratory experiments? So we have flavor oscillation experiments that tell us that neutrinos are massive. Okay, so let's say they tell us that at least 2 of the 3 neutrinos are massive. Okay, then we don't know about the lightest mass eigenstate. So we know the mass differences from the oscillation experiments, and we have 2 possibilities for the ordering of these masses, which are called normal and inverted ordering. So one possibility is that the 2 lightest neutrinos are the ones that are closer in mass, and they have a heavier and let's say farther neutrino, or the other way around. So the two neutrinos which are close in mass, so the small mass gap corresponds to the heaviest, so to the 2 heaviest neutrino mass eigenstates. So this is called normal, this is called inverted. So we don't know whether we are here or here, okay? And we don't know what the gap between the lightest eigenstate and 0. So in any case, even if the lightest eigenstate is in 0, the 2 heaviest, they are anyway not relativistic, in the sense that they have an energy, they have a mass which is larger than 10 to the minus 4 eV. So then if you use the results from oscillation experiments, you have that the sum of the masses, it's either larger than 60 millielectron volts if the ordering is normal, or 100 millielectron volts if the ordering is inverted. This is the number that you get by putting 0 for the mass of the lightest eigenstate, just that. And then this means that also your omega nu h squared has some lower bound, which is anyway very small. So we know that in any case, neutrinos today, they might make some, they definitely, I mean, they should be there, okay? And this is the lower limit on their density parameter. We also have upper limits, as I will comment in a second. So, again, just to remind you, this is what I just said, just to remind you that the discovery of neutrino oscillations and then of the fact that neutrinos have a mass was worth the Nobel Prize in 2015 to Cauchy and McDonald. Now, as I told you, we don't know that gap, okay, between 0 and the lightest eigenstate. So if you want, we don't know the absolute mass scale. We have a few ways of searching for that in the laboratory. You can look at the endpoint of the spectrum of the beta decay of tritium, for example. And this is the current limit that we have on the mass of the electron neutrino, 0.35 eV. This is an experiment called Catherine, which is going on now. Or you can look to some exotic beyond the standard model process, which is called neutrinoless double beta decay. And here you get a constraint on this m beta beta parameter, which is in the ballpark of a few tens of millielectron volts. But again, this is not really the neutrino mass. This is related to the neutrino mass in some non-trivial way. You can read that from this plot. I'm not going to dig too much into that now, but here you have the mass of the lightest eigenstate and this m beta beta parameter. So these are the 2 ways through which you can look for neutrino masses in the lab. Another one, as I told you, is in cosmology. Why? So the reason is that neutrinos, as I told you, they do free stream. So if you have seen some other talks from me, you have seen probably this picture quite a few times by now. So this is the cosmic web. This is the distribution of matter in the universe from a simulation, from a computer simulation. This is a box of 1.5 million light years. The difference between these 2 plots, these 2 fields here, is that they evolved from exactly the same initial condition. Okay, but this is a universe where there are no neutrinos, and this is a universe where there is a very heavy, actually, there are very heavy neutrinos, nearly 2 eV, which we know it can't be, also from laboratory experiments, but again, this is just so that you can appreciate the difference by eye. So this corresponds to a density parameter of, I think, 4 in 10 to the minus 2. So what's the difference here? The difference is that here the field is somehow smoother. Okay? So here, if you look at the at the variance, okay, of density fluctuations, it's definitely larger here than here. What's the reason? The reason is, again, that neutrinos, they are very light. They move at nearly at the speed of light for a big part of the cosmic history. So they are able to basically escape potential wells. And this means that the matter distribution is somehow smoothed. So you see this because you have some initial overdensity and matter, which is typically very cold, both ordinary matter and cold dark matter. That's why we call it cold dark matter. Have negligible dispersion velocity and can fall into the potential. I mean, starts forming potential wells, and these potential wells, they grow relatively fast, and matter can fall into the potential wells. Here you have part of the matter that is constituted by neutrinos, and neutrinos, they have basically an escape velocity, so they move fast enough that they can somehow escape the potential wells. This effect becomes larger for larger neutrino mass, just because the energy density in neutrinos is proportional to the neutrino mass. So this is the same effect seen in Fourier space. Okay, so in the power spectrum of perturbations, everything, just look at the dashed lines, everything here is normal. Again, this is the variance, okay, of density perturbations at a given scale, at a given wave number. So small scales are on the right, large scales are on the left, and you see that, and everything is normalized to a universe without neutrinos. So you see that at very large scales, everything looks the same. So if I were to pass a low pass filter here, okay, and only keep the low frequencies here, okay, these two images will look the same, okay, but at the high frequencies, the high spatial frequencies, they look very different. And again, the larger the neutrino mass, the bigger you find a suppression, okay, at small scales. Look, for example, at you cannot see some of the curves, but look at this, for example, which is for a 1 eV sum of the neutrino masses, and you see this kind of big, okay, this is a 40% suppression, okay, of the density fluctuations of small scales relative to a universe without neutrinos. So how do we probe this? Of course, this is an effect on matter, on structure formation. So we can either look at the galaxy number counts, for example, or at the weak lensing of the galaxies and the cosmic shear, but we can also look at the CMB. Why? Because the CMB, it's true that it's emitted at a very early time, but again, the CMB light has to go through this matter distribution. Okay, so if you let the CMB go through this matter distribution or this matter distribution, it will look different, because you have a weak lensing effect, okay, which is stronger when you don't have neutrinos. Again, because you have a larger variance of the fluctuations.
What's the difference? Can you go to the next slide, please?
Next, you mean this one?
No.
What's
the difference between the solid and dashed line?
The difference between the solid and dashed is that the solid, the dashed, you are keeping everything constant at the level of cosmological parameters, and you're only changing the neutrino mass. Okay. In the solid lines, you are keeping things fixed. So to basically, you are kind of imposing a Planck prior here. In the sense you are changing the neutrino mass, but you're also changing other parameters to keep the quality, let's say basically to keep the first peak of the CMB fixed, more or less. So you are taking some quantities which are very well constrained by the CMB, like the time of equality, the sound horizon, the length of the sound horizon, and you are changing other parameters like the mass and probably the Hubble constant to keep those constant when you also vary the neutrino mass.
Okay. The point of the picture is that no matter what convention you choose, then as you increase the mass, total mass of neutrinos, you suppress the
Yeah, exactly. The point is also, if you want, there is also a more subtle point, is that when you do a combined analysis of CMB, primary CMB, plus some probe of the large scale structure, the large scale structures data, the model will try to adapt to this in some sense. No, because the CMB is fixing everything else somehow. Okay, now what's the what's the situation now? So we can constrain the neutrino mass. From Planck, you get these numbers here. So you get these sum of the masses less than 0.24 electron volts. If you add, this is just Planck, so this is a combination of these observables here. You can add some geometrical information that I will describe in a second that comes from galaxy surveys, and you get this number here, which is very close to the upper limit, to the lower limit from inverted hierarchy, okay, which is 100 milli-electron volts, and this is 120. Okay, now, again, we also have information from large-scale structures. Let me just mention the most recent data that we have. They come from this instrument. You might have heard of it because they made the news a couple of weeks ago. Actually, I think it was the same day on which this seminar was originally planned. There was a series of data release on the day in which we were initially planning to have a seminar, and that's the reason why we're having it today, not 2 weeks ago. By the way, so this is a telescope, okay, that is mapping the distribution of galaxies in the universe. So they had a first data release 1 year ago, and the second data release with 3 years of data a couple of weeks ago. This is the largest map of the universe that we have available today. And again, what do you get from this? So you get, again, this, you get somehow this information on the power spectrum. You also get some geometrical information. So what's the geometrical information? The geometrical information comes from the fact that if you look at the distribution of galaxies, there is some characteristic length that is imprinted in the distribution of galaxies. Okay? So there is a peak in the 2-point correlation function. So the effect here is somehow exaggerated, but the point is that if you have a galaxy here, okay, and you think about the probability of finding a galaxy at a given distance from this white region here, okay, so the probability does like that. So it goes down, but it has some peak here at around a common separation of 100 h to the minus 1 megaparsec. Okay, so this means that, again, there is somehow some kind of excess probability, okay, in this ring here with respect to this smooth behavior of some exponentially, it's not really exponential, but some power law decrease, okay, of the probability. And the reason is that, again, there is a characteristic scale that depends on baryon acoustic oscillations, which is why this is called baryon acoustic oscillation. So this is an imprint of the primordial baryon acoustic oscillations in the galaxy field. If you want this length, it's the same that sets the spacing in the peaks of the cosmic microwave background. So why is this important? Sorry, because this is a standard rule. So these should be, again, at 100 inverse megaparsec, more or less independently of your cosmological model. Okay, not really. I mean, you have the cosmological parameters entering, but you can compute these as a function of the cosmological parameters. And you see the same thing projected on the sky, so under a given angle. So you observe the angle, you know the scale, and you can tell how far this object is. Okay, the usual, you can compute the angular diameter distance of this field. Now, then this gives you a very strong handle, okay, on the expansion history, which is something that somehow acts as a confusion noise for your estimate of the neutrino mass. And so you already see this here, no? That basically when you add this BAO, so this BAO here is not the DESI1, okay, this is an oldest data set, but you get a factor of 2 in your constraints. Now, the interesting thing here is that again, so this is what you get from the CMB alone, the yellow line, okay? And this is already somehow peculiar because this is peaking at 0 mass. So we know from oscillations that the mass has to be at least this, 60 milli-electron volts for normal or 100 for inverted. But the point is that when you add this DESI BAO, you get this. So, I mean, these curves, there are slightly differences in the analysis here, but they're basically, they all tell you the same thing. And the number that you get is this, which again is kind of strange because this is really, this is excluding inverted hierarchy at some level. I don't remember, it was the statistical level, I think 2 or 3 sigma. And 3, probably something around 3. And this is also kind of challenging the normal hierarchy. So if you take this at face value, it seems that the unit, the cosmological data really this cosmological data, this combination of cosmological data really likes to be fitted by a universe where there are no neutrinos, okay? And actually, if you somehow extend this to negative neutrino masses, of course the neutrino mass cannot be negative. But if you try to somehow account for an anti-smoothing effect, okay, so you know that increasing the neutrino mass will smooth your distribution. You try kind of to reverse this, and you call this a negative neutrino mass. The peak will also move to negative neutrino masses. So this is something that has been people have been thinking a lot late in the last year, because this was also present with the first data release 1 year ago. We know what are the features in the data to some extent that cause this. We know that the CMB data have somehow a higher lensing that you would expect in the standard model. Also, the DESI data prefer a low density of matter and a high value for this combination of parameters. And so this is the reason why basically you get this, which maybe it's not an explanation, but let's say we know where it comes from. Now, you might have heard that DESI made the news because they find evidence for dark energy. Okay, they find a preference. Evidence is probably too big a word. They find preference for dark energy. For evolving energy, for dynamical dark energy, which I'm not going to talk about in this talk, but the point is that this is the same thing, in the sense that this data here, this probability distribution here is obtained with a cosmological constant. So there is no dynamical dark energy here. When you try to fit for both dynamical dark energy and neutrino masses, you find this. Okay, so something that is still, peaked in 0, but of course the width of the distribution, of the probability distribution, is increasing, okay? And everything is more compatible with oscillation experiments. You can think of this as a tension between cosmology and oscillation experiments.
Okay. Does that go in the direction of preferring a cosmological constant as well?
No, if you do this, you find the dark energy, the dynamical dark energy.
Okay.
So this is when you fit for both neutrino masses and dynamical dark energy. Okay, and then you find again the preference for dynamical dark energy, but neutrino masses go away. The small neutrino masses that don't really go away, but these get diluted. So this is how we're saying that whatever is responsible for the preference for dark energy is also what is giving you the preference for very small neutrino masses when you fix the dark energy to be a cosmological constant. So whatever feature in the data is giving you one is also giving you the other.
What is baseline here?
Baseline is Planck plus ACT DR6 lensing. Is Planck primary plus Planck lensing plus ACT DR6 lensing. That was because ACT DR6 lensing was released 2 or 3 years ago. Okay. So if you want, it's the most constraining CMB data set that you can build, that you could build before ACT-DR6 primary came out.
And all the others are the same CMB plus the extra.
Yeah, because there is also some dependency on the. Okay, this is on the DESI plus CMB. But the point is that when you add the supernovae data, okay, things go back to 0. You also find a stronger preference for dark energy, but there is some dependency on the data set, as you see. Okay.
But we agree that this is flagging another sort of tension with the supernovae data.
Sure. Yeah, but again, the result in the previous here and the black line. All the curves here, okay, and the black curve here, they don't have supernovae.
The black.
Yeah. No, but I agree that there is something something strange with this, something strange going on with the supernova.
Okay.
They have a plot which I don't have here, in which they take the
When you say attention with the supernovae? Supernovae don't have any leverage on WA.
No, I mean that there is some, let's say, no, okay, let me put it like this. The point is that if you look at the DESI data, if you look at the expansion history that is preferred from by the DESI data, and you plot the supernovae measurements over that, okay, you will find that some supernovae measurements, no, they agree with that, and some other are at variance. And I think that the one that is most at variance is probably Pantheon, I think. Which is why you get the smaller constraints, because you are trying to fit things that are not in complete agreement.
There is still the, sorry to insist, there is still the 0.7 redshift in the DESI data that was problematic.
No, yeah, because in the very first year it seemed like everything came out from one single bin. No, now that has kind of gone away. Okay. So let me also mention this result, which is somehow related. So again, more or less on the same day, we had also new data from this experiment, which is the Atacama Cosmology Telescope, which is a CMB observatory from the ground in the Atacama Desert that again released the legacy data. So here again they have some combination with different. I mean, either just with Planck, which is the blue line here, okay, or they do combine with lensing and again BAO and baryon acoustic oscillations, and so they consider different data sets for the BAO. So you see also here that if they fit with the BOSS, which is another survey, they find this curve here. Okay, while when they fit with DESI, with the first year actually DESI data, because this was done before, they came on the same day, so this was done before the DESI data, 3-year data came available, you get again this strong constraint, but maybe we are seeing basically the same thing here as the other plot, okay? And again, the bound is 80 millielectron volts. So now forgetting for a second about this this tension, let me try to put things in a context. Unfortunately, this is not showing as it should, but by the way. So one thing that you can do is that you can put your constraints on this plane. So this is again this m beta beta. This is the effective Majorana mass of the neutrino, which is the quantity that is relevant for double beta decay, so for some laboratory search. And this is the sum on neutrino masses, which is what is constraining for cosmology. Now, oscillations, they somehow give you a relation between these two things. So oscillation experiments, they give you some relation, which is not one-to-one, because there is some extra parameter that oscillations are insensitive to. But in any case, they give you a band. This is why you see two bands here. And one band is for normal hierarchy, and the other one is for inverted hierarchy. So this is not showing correctly, because this should go like this, okay? Which is for normal hierarchy, and this one should go like this. Now you can, it's nice now that you can somehow, you can, if you want, you can use cosmology, constrain the sum on neutrino masses, okay? And given the oscillations, that will give you some constraint on m beta beta, or the other way around. You can get m beta beta, okay? Draw a line and then get a constraint on the sum of neutrino masses. And it's nice that the constraints that you get like this, they are more or less on the same ballpark. They are compatible, first of all, and they are on the same ballpark. So there are different constraints here. Again, for the cosmology, this depends on the BAO data set that you use. for lab searches, there is some uncertainty related to nuclear physics. So this upper limit somehow can move up and down between these two values. Okay. But again, I think this really shows a nice how these measures are complementary. Okay, now I'm really late as usual, but we started nearly 10 minutes late. So long for the masses. What about an effective? We also want to measure an effective. An effective has a characteristic effect on the CMB at small scales, at large L's. So this is the CMB power spectrum. For those of you who are familiar with the plots of the CMB power spectrum, there is an additional factor of L squared here to make more evident what is happening at large L's. And again, here I'm plotting a model with an effective equal to, this is 3.46, because this was the result of the theoretical calculation when I made this plot the first time, and you will never see the difference by eye between 46 and 44. And then you see I'm varying an effective, and this is how the spectrum will change. And the black dots are the Planck measurements of the power spectrum. Then this, as you might expect, this gives you a quite good constraint, okay, 5% precision on an effective, which is 2.89 plus or minus 0.19. So this is perfectly compatible with the theoretical expectation. You also see that, first of all, the experimental precision is much larger than the theoretical precision, which was 2 × 10⁻⁴, I think. And also, it's still quite larger than the difference due to non-instantaneous decoupling, okay? So, which is 0.044. Now, this is already telling you something, no? Because if you think about it, we all expect, we are all told repeatedly that there should be new physics beyond the standard model, so we expect new particles. Some of these particles are light enough, or they should be light enough to be produced in the early universe, to be made in thermal equilibrium, and then to contribute to this number. So in some sense, the fact that you really get the number that corresponds just to 3 neutrinos is somehow amazing if you think about it. Or in any case, it's a big success of the model. For example, you can already exclude that there is a fourth thermalized neutrino species. Now, this doesn't mean that you cannot have a sterile neutrino in general, in particle physics, no? It's just that if you have this fourth neutrino, or maybe even a fifth or a sixth, they should never come up in thermal equilibrium in the early universe, so that their density is kept low enough, because again, this is not really a measure of the number of particle species, it's a measure of density. So if you have your species that are at a low enough temperature, you are fine. Okay, again, this is what I was saying. No, so why are we looking at an effective? Because that's an indication that things are not going as we would expect in that simple picture at the beginning. So you can have an additional particles like sterile neutrinos or thermal axions. Might be that you have a no standard expansion history, like a low reheating temperature. So, like for example, in that very long timeline that I showed you, maybe everything started at 10 MeV, okay, and not at 10 to the 17 GeV. It might be that neutrino decoupling is not going on as we think. One possibility is that you have interactions of neutrinos with electrons, non-standard interaction, that are keeping neutrinos in thermal contact for a longer time. That's actually a very powerful way of constraining these kind of interactions. Later, I'm going to talk about another kind of non-standard interactions, which are not this one, so just telling that to avoid confusion. Or you might have also a large lepton asymmetry, so a chemical potential for the neutrinos. Okay, so what is the current situation? So this is again so this is the situation just with Planck, the dashed line. So this is actually, Planck plus Lensing plus BAO, but BAO, they're not that important in that measurement. They help, but they're not that important. And you see, this is more or less the number that I told you before. The new data from ACT, they have a preference for an effective which is smaller than 3. Is actually still compatible with 3, still compatible with Planck. but it's smaller. It's 1 sigma away from the standard expectation. I wouldn't get too excited about that, honestly. I wouldn't charge that with too much meaning, okay? But if you want, the error bar goes down by a factor of 30%, more or less. And if you want, these are the different measurements of an effective from various data sets at a glance. Okay, now, why is, okay, another way of looking at an effective, again, is to look at extra species. Okay, so if you have some other particle, as I was saying, like an axion or a sterile neutrino, that was at some point in the early universe, okay, so with couplings to the standard model, which are large enough that this particle is brought at some point to thermal equilibrium, then that should contribute to an effective. But how much? Of course, that doesn't contribute as one. Why? Because they are not necessarily at the same temperature as the neutrinos. And the reason is the same as the reason why neutrinos are not the same temperature as photons. If this particle decouples very, very, very early, then every time a particle species of the standard model annihilates away, it will transfer electrons to the photons and to the neutrinos. So everything will be heated up, but this extra particle. Okay? Then the earlier the particle decouples, which means the smaller are its coupling, and the less it will contribute to an effective. And you see this basically in this plot. Okay, so here again you have the temperature at which the extra species ceases to be in thermal contact with the plasma, with the standard model plasma. Various curves are for a different kind of particles, I mean, different number of boson and fermions with a different number of spin degrees of freedom. And you see that as and this is that kind of effective, okay? So the extra and effective contributed by the species. So you see that when the temperature, the decoupling temperature goes down, okay, the contribution to an effective goes up. So these are the current constraints. So this is again the constraint, this one here below is this. So again, this should be shaded as well. And this is the Planck alone constraint. And this is the Planck plus ACT constraint. And you see this is somehow excluding particles that stayed in thermal equilibrium too long. Okay, so we cannot stand, from the point of view of the data, a particle that stays in thermal equilibrium until below 100 MeV. Okay, so if there was something that was in thermal equilibrium, it has to decouple at a temperature larger than 100 MeV. And again, you can substitute this somehow. If you have a theory, a Lagrangian, you can substitute your coupling somehow here. So large couplings are here, small couplings are here. Okay, so this can be translated once we have a theory as a constraint on the coupling. Okay, now what about non-standard interactions instead? So everything that I've been telling you now is not changing one fact. So the fact that we assume neutrinos to be free-streaming. So neutrinos after MeV, they stop interacting not only with the photon, but also among themselves. Okay, so every neutrino just goes on a geodesic. This can be changed. So this is something that I didn't say, sorry, that we participated to the ACT analysis. I should say this. People in this in the cosmology group, in particular Martina Gerbino, Luca Pagano, Nicola Barbieri, who's sitting here, and myself. And I was reminded of this because this is Nicola's work. This is mostly Nicola's work, so you answer questions in case. And so what's the idea here? The idea is that you have theories in which neutrinos have self-interaction. So again, this has nothing to do with the electron-neutrino interaction of neutrinos with electrons. It's just interactions among neutrinos. This means that neutrinos, they still go out of thermal contact with the plasma at MeV, but they are collisional. They are not free-streaming. They stay collisional for a longer time. So you can think very roughly, I mean, this is a cosmologist representation of the Lagrangian. So you have a 4-pointer. I mean, if this you have some heavy particle that is mediating the interaction. So at low energy, this effectively looks like a 4 fermion interaction. So this is exactly like the Fermi interaction, just with a G effective in place of G Fermi. And this G effective is the fundamental coupling, the dimensionless coupling square over the mass of the heavy particle that is mediating the interaction squared. Now, this is a class of models that has been studied a lot because at some point it was thought that it might help solving the Hubble tension. Now, this claim has been somehow disproved by more accurate data. But still, these models are interesting also because we see that we can put constraints on this G effective, so if you want, on this combination of quantities, which are somehow competitive with constraints from the lab. And this is what you get when you fit for this G effective the ACT data in combination with Planck. So let's say that again, without going into the details, you have two regions, one that we call mildly interacting. So you have a preference for a non-zero interaction strength, but you see that this probability curve here does not go to zero. So I mean, let's say that everything here is compatible with lambda CDM. Now you have another region here in which there is a peak at relatively large values of the interaction strength. And again, this was done because in the past it seemed that this region here was preferred over this region here. People were excited by that. Again, later data have disproved that, and also the ACT data, they don't show any preference. So you don't see this here because this, you see there is a break here. So these two regions, they are not analyzed together. So you shouldn't, the relative height, there is no information here about the relative height of the two peaks. Okay, so we did a chi-square analysis, and this is in any case disfavored at the 2 or 3 sigma level with respect to this region here. Okay, so everything is compatible with non-interacting neutrinos, but still, if you put things on a plot, this is this region here is what is excluded by ACT, and this is kind of complementary to what you get from laboratory experiments, which are these regions here. That also depends on whether this phi particle is coupling to electron, muon, or tau neutrinos, and you get different bounds. For example, the bounds from tau neutrinos, for tau neutrinos, are very weak from the lab. Okay. Now, very quickly, the very last slides about the future. So there are several experiments, and on which the people in the group are working. I mean, to a different extent. So one is Science Observatory, which is another experiment in Atacama, which is basically had first light in a few weeks ago, and it's an experiment that is designed to measure the CMB from the ground, and it's an improvement over third generation experiments like ACT. This is this is a generation 3.5 experiment. Then we have, let me go first to CMB stage 4, which is a stage 4 experiment, which again is an experiment. This is some things here about this are a bit outdated because this is an experiment that was should start in the 30s, and the idea was to have several telescopes at the Atacama Desert and at the South Pole. Now the project is kind to be reformed because it's not clear whether South Pole is still a possibility due to some choices of the US government. So basically, the collaboration is studying an option in which you don't have telescopes at the South Pole, but only in Atacama. In any case, this is another improvement in terms of noise with respect to SO and to the third generation experiments like ACT. Then, on a completely different kind of experiment is LightBird, which is a satellite Okay, so it's observing a different range of scales. Is observing the large scales. And also Lightbird is undergoing some reforming process after some changes that happened, okay, over the participation of KK. But again, Lightbird is expected to measure the anisotropies, the semi-anisotropies at large scales, which are not directly relevant for the neutrinos, but are indirectly relevant because they help to break a degeneracy with other parameters. Then different kind of experiment is the galaxy surveys. So we have Euclid in particular, which is taking, again, data now. There was a first data release 2 weeks ago, which was a quick data release that was meant, to let people, let's say, familiarize with the data. So there was not too much. There was some scientific exploitation of the data, but not that much. So the first data release is happening next year. And again, Euclid will give us information through the galaxy number counts and the cosmic shear. So, for example, what you can do with all these things together for the neutrino mass. So again, this is what you get if you look at the dashed contours when you take the Planck data. So if you take Planck, you combine that with a measurement of the small scale CMB, like the one from CMBS4, and with BAO, like the ones from DESI or LSST, which is or Euclid, you will get something similar. There is no Euclid here, but you will get something similar. This plot is used to show the kind of degeneracies that Lightbird is breaking. Okay, so these are 1 sigma contours. So you get something. You get a measurement of the neutrino mass at 1 sigma. If you don't use Lightbird, if you add Lightbird, you get a 5 sigma measurement because you break the degeneracy with this other parameter, which is the reionization to optical depth. Okay, this is the same plot as before, and again, you see the improvement that you get from CMBS4 that will measure an effective at the 2% level. Okay, so this is the expected error is 0.06. And again, this is how then you can improve your constraint on the freeze-out temperature of very, very light species. Another possibility, okay, to produce light species, and this is really my second to last slide, is a scenario in which your species was never really in thermal equilibrium, but you have some very tiny coupling that is effective for a very long time. So one example is the magnetic moment of neutrinos. You can have magnetic moment of left-handed neutrinos, and if neutrinos have a magnetic moment, sometimes you have scatterings in which you start with a left-handed neutrino, you scatter off an electron, and the final state neutrino is a right-handed neutrino. You have an LCT flip, okay, which is mediated by the magnetic moment. Let's say like this. Then you start with a purely left-handed ensemble of neutrinos, and in due time you build up some density of right-handed neutrinos, okay, which is what you see here somehow. So this is the same plot as usual. So here you have the coupling, which is the magnetic moment in units of the Bohr magneton, and this is the delta effect. And the larger the magnetic moment of neutrinos, the more right-handed neutrinos you produce, and then this gives you a contribute to delta effective, which cannot be as large as you want. It's bounded by the data. So this will give you a bound on the magnetic moment of neutrinos. And this is again a plot in the, let's say, this is the magnetic moment. This is the scale of the physics that is responsible for the neutrino magnetic moment. This is the current constraint, and this is how the constraints will improve with next generation experiments. And the strongest constraints, for example, from the lab are around here, okay, around 10 to the minus 11 Bohr magnetons. So this is really a big improvement. There is, of course, some model dependency, but I think it's an interesting thing to look at. Or similarly, you can have axions that couple very weakly to photons. And again, given a coupling, if that acts for a long enough time, you will build up some primordial population of axions that will contribute to delta N effective. And again, you see this in this curve. And again, you can use this to constrain the coupling of axions to photons. This is something that we did with, let me tell you just yesterday, with Martina Gerbino and then with Luca Caloni and Patrick Stengel, who were both postdocs here. Luca now is in Coimbra, a postdoc in Coimbra in Portugal, and Patrick is in Ljubljana in Slovenia. So this was my last slide. I don't have a summary. I'm just thanking you because I took quite some time.